We actually can't do pointers to references. So we're going to have to adjust this. This is mistake number 3 now. I'm going to keep track of how many mistakes. Instead of returning a address to a cell, let's just go ahead and return a pointer to the cell. That'll make this easier. And there we go. We just need to go into the header file and change that to a star. Yes, this is going to be a long video. Sorry, chaps. And cell star cell equals get cell. And now we can say owner cell equals cell. And here we need to say cell arrow balls.pushback. Simple change. All right, so now each ball knows what cell it belongs in. So when we go to ball controller, when we move it, we can determine if it needs to go to a different cell. So here we go. We loop through each ball, and let's see, do we handle collision? We do handle collision in the same spot. So I'm going to take this out. We're not going to handle collision on the first pass. The reason we don't want to handle collision on the first pass is because it's going to make it a little bit more difficult. And if we just loop through our ball's vector for movement and loop through our grid for collision, it makes things a lot better. You won't get double updates or things like that. We have to be worried about updating the same ball twice if a ball is shifting between cells. Okay, so I lost my train of thought. What we're doing is we're looping through balls, and right, we are checking to see if its position changed, or if its cell changed. So what we're going to do is call grid get cell, and we're going to call it on ball.position. And what we're going to do is store that in a new cell pointer. So we'll say cell star new cell equals that. We'll say check to see if the ball moved. Now we're getting an error here, and the reason we're getting an error is because we haven't included grid.h. Remember, we used a forward declaration, so in the CPP file, when we actually use it, we need to make sure we include grid.h. And ball.position is error call of class type without appropriate operator, because I put parentheses. It's not a function. All right, so now all we got to do is say if the new cell is not equal to ball dot owner cell. Now if that's the case, then we need to actually move the ball. Need to shift the ball. And to do that, what we need to do is remove it from its vector in the cell that it's currently in and put it in the vector of the cell that it's going to, and we also need to change its pointer. Now we have a problem here because when we want to actually remove the ball from its cell, if we go to the definition of the cell, we'll see that it's a vector. Now removing a given pointer from this vector means we have to loop through the whole vector, which is going to, at worst case, mean we have to loop through every single element in the vector to remove it, and that's not very good at all. Instead, what we can do is we can use a little trick that I want to show you guys. We can keep track of our location in the vector so that we can look up our position immediately. So what we can do is say int, and we'll say cell index, or cell array, cell vector index. Super descriptive. We'll start that out at -1. And whenever we add a ball to the cell, we're going to set this cell vector index equal to its position in that vector. So when we want to remove it, we know exactly where it is, and we don't need to loop through the whole thing. This means our ball class is a little bit bigger, but it's not too big of a deal. So let's go back to what I was doing in ball controller. Oh, no, we need to make use of that first. We need to go to grid.cpp and make sure we're doing that correctly. So we're going to say, here we say cell balls push back, ball owner cell equals cell. Now we need to say ball, let's see, ball index, ball owner. I have terrible memory. Cell vector index equals, and we're going to say cell dot or arrow balls dot size -1. And that's its position in the vector if it's at the back of that vector. And that's awesome. One thing you can actually do is utilize this technique here, storing a vector index, to eliminate that issue with pointers to balls in that vector. By instead of storing pointers to balls, you store indexes of balls. And that's something you can do to fix that and remain cache friendly. Okay, so now we're setting the vector index. Now we need to have the ability to remove a ball from a cell. So void remove ball from cell, and we're just going to pass ball star ball, and we don't need to say which cell we're removing from because we know we're removing from the cell that is stored in the ball. So let's implement that. Right click, refactor, create implementation, get Visual Assist, it's worth the money. There is a free trial though. Okay, so to do this, first we need to remove ourselves from that cell. So we're going to say ball arrow owner cell arrow balls, and what we want to do is do the vector swap that we usually do to remove something from a vector, because remember the vector swap is the fastest thing you can do. So we're going to say ball owner cell balls, and the index is going to be ball arrow cell vector index equals ball arrow owner cell arrow balls dot back. Now this is a big line of code. We can make this a little bit easier to read with a little trick here. We can say, let's see, what is balls? Balls is a vector. We can say std vector ball star, and then ampersand, we're going to make it a reference, balls equals ball owner cell balls. And now, what's going on here? Vector balls, vector ball, balls equals ball. Ball looks weird after you look at it for a while. Balls, no, it's not. Shut up. There. All right. So now we can replace ball owner cell balls with balls. I have been saying balls a lot lately. Don't make fun of me. All right. So now we this is our normal vector swap. Normal vector swap. And then we call balls dot pop back. But there's one more thing we need to do in addition to this normal vector swap. Since we moved the ball from the back into our new position, we need to update that ball's vector position. So we're going to say ball update vector index. We're going to say balls ball cell vector index equals ball cell vector index. And finally, set the index of ball to -1. That will specify that we are no longer in a vector. Balls or ball dot cell vector index equals -1, and also we might as well, just for safety, say ball owner cell equals null pointer, because remember, null pointer access violations are easier to debug. Because this should be arrow or dot arrow cell vector index equals that. All right, now we have the ability to remove a ball from the cell. Super cool. Now we can go to main game. No, ball controller, and we can actually move the ball to the new cell. So what we're going to do is say grid dot remove ball from cell, and we'll say ball. And ball is a reference again. Oh no, ball is a reference. So we're going to have to say the address of ball is I, because you can't say the address of ball. You can't actually take the address of a reference. That's just something you can't do in C++ for safety reasons, I believe. So the address of ball is I. That will remove that ball from the cell, and now we can add the ball to the new cell. So we're going to say new cell arrow grid arrow add ball of balls I. And now add ball is actually doing a little bit of extra computation to get the cell that we've already done. So let's make another overloaded add ball. So adds a ball and determines which cell it belongs to. And we're going to make another one. And this time we're going to pass in a cell. Cell star cell. Adds a ball to the specified cell, because there's no need to do that computation twice. We should cut corners wherever we can. And we'll do that here. There we go. So now all we got to do is cut out this first step of cell get cell. And to make our code even smaller, what we could do is call add ball with the overload from here. Ball cell. Now there might be a slight function call overhead for doing this, so that's the reason I'm not going to do that. It might get inlined by the compiler, but it also might not. So just to be safe, I'm going to duplicate this code, just because this is a function that's going to get called a lot. Okay, now add balls I, and we're going to say new cell, and this should be the address of balls I. And that should handle moving the balls between all of our different cells. So that's all we've done so far. We're no longer doing any collision. I'm going to just comment this out. So our balls should just bounce around the screen. Let's just see if it crashes, because if it crashes, we've done something wrong. You should always do error checking as you go. Update balls does not take 4 arguments because we need to pass in mgrid. Now, the parameter here is a grid star, but remember mgrid is a unique pointer, so we're going to say dot. Remember, not arrow. Arrow is when you want to access the grid. Dot is when you want to access the pointer. Call mgrid.get. All right, now we can run it. Cell, ooh. Well, first of all, we have a bug there. But second of all, we had a warning when we were building. Cell first time seen using struct, now using, or class, now using struct. It's because when I forward declared cell, I said class cell, but it's actually a struct. So that's why you really got to keep an eye out for those warnings. That can actually be a pretty bad bug. Now, where the heck did I do that? Was that in ball constructor? Was that in, let's just control F, class cell. Entire solution. There it is in ball.h, struct cell. There. Now let's run in debug mode and see where it crashes. Maybe that caused the crash. That's actually possible, I think. And we got more warnings. Vector subscript out of range. Break. And that is happening in add ball on init balls. Okay, so that should be actually really easy to debug. I've taught you guys all about debugging in some of the previous tutorials. So ball position is 1680. In X and Y. So let's see. Get cell is failing. Cell X is 8. Cell Y is 8. What is our dimensions? We have num X cells is 15. Num Y cells is 9. That sounds about right. Y times num X cells plus, that's probably the issue here. And yes, I believe that's the issue. It's not plus m num x cells, it's plus x. That's definitely the problem. So now we can run it and it should be good. Where are we getting it now? This is in remove ball from cell. Cell vector index is 0. I'm going to pause the video on this one because this one doesn't immediately spring to mind. Okay, I figured it out. It was actually pretty simple. The way I debugged this is I just printed out the balls.size before I removed the ball. And whenever you run it consistently, every time it crashes, it's a 1. And the reason that it's always crashing on a 1 is because, let's remove IOStream up here. If we go to, where is it? Grid.cpp, where we remove a ball from cell, here we are assuming that there's any balls left in the cell. If we call balls.pop back here, and that ball was the last ball in the cell, then there's no way we can actually change the cell index here. We're going to get a vector access violation. So what we need to do here is say if balls.size, or alternatively, if not balls.empty, whichever feels more readable to you, then we update a cell. Because if there's no balls left in, then we can't try to dereference it here. And actually, if that's actually another point. This will still be a bug if this is the last ball in the vector. So an easier, a better way to check this would just be to say if ball cell vector index is less than balls.size. So if balls.size is 0, this will always be false. And if the ball is the last ball in that vector, then this bug won't happen. I hope that makes sense. So now let's see if it crashes anymore. It doesn't. Good. So now all of our balls are happily bouncing around and they are shifting their grid positions and everything. We're still getting a steady 60 FPS. They're not colliding because we did disable the collision code, but I can fling balls around and make them bounce. I need to stop saying balls so much in this video. All right, so now let's implement collision, and then let's see how far we can crank this up to. I want to get at least 10,000 balls. So let's see what happens. Oops, let's go back here and close that. All right, so now what we need to do is handle collision in our ball controller.cpp class, and the way we're going to do this is we're going to loop through every cell and just update each cell. So let's go ahead and make a function for handling collision. And check collision, actually, we're going to change that. It's not going to happen. We'll have a check collision, we'll have an update collision. So we'll get rid of grid from that, but we'll have an update collision that uses the grid. Void update collision. And we're going to say ball, no, we're going to say grid star grid. Updates collision. Totally unnecessary comment, but I did it anyways. Now we can implement this. We'll implement it above check collision. So let's go there. And here we go. Here we go. Check collision. And let's do ball controller : here. All right, so now here's where we have to worry a little bit about performance. Now, depending on how many cells we have, if we have a ton of cells, right now we're going to be iterating through every single cell in the grid. Now, there is an optimization we can apply, and I might apply it at the end of the video and just show you guys that'll prevent us from having to iterate through every cell. We'll only iterate through cells that have a ball. But for now, we're just going to iterate through every single cell and update them with all of their neighbor cells in the L shape. To remind you, this yellow L shape around the purple box, including the purple position. All right, so first let's iterate through all of the grid spots. So we're going to say for int I equals 0, I is less than grid dot. Right. We can't access the cells of grid because it's a private variable. However, I feel comfortable making the ball controller a friend class of grid. So we're going to say friend class ball controller, and you can really put this line anywhere you want in here, but I'm going to put it here. So now the ball controller can access all of these variables and do whatever it wants with it. However, no other class can. So we still get encapsulation here. We could have written a bunch of getters, a bunch of getters and setters, but that would mean that any other class could modify it, and it would be just like public variables. All right, so update collision. Here we go. Now we can actually loop through m. Let's see, m cells dot size, and we'll say I++. Now the first thing we need to do is determine what is our x and y position at this given cell. So we'll have int x and int y. So how do we determine this? Well, we just use a little bit of arithmetic. I is the index into that one-dimensional array, but we need to treat it as a two-dimensional array. For the x position, we just say int x equals I modulo, hopefully you remember modulus division, it does division and returns the remainder. We're going to do modulo grid arrow m width, or m num x cells. Yes, m num x cells. For the y position, we're going to do an integer division. We're going to say I divided by grid m num x cells. In both cases, we're using m num x cells. This is not a bug. So this basically says how many rows do we have. Since these are both integers, it'll do an integer division. That's what we want. And this says how far into a given row are we, and that's our x position. So now we have x and y. We can do stuff with it. So what we should do is we should loop through all of the balls in that cell and check their collision with all of the other balls in that cell. And we should also do the same thing. We should check the collision with each of those balls with all of the balls in the adjacent cells. So first, let's loop through all of the balls in our current cell. So we're going to say for int j equals 0. J is less than grid arrow. And actually, we don't actually need j here, I believe. We don't need it, so we'll just use a for each loop. Could be wrong, but we'll see. For auto, for each loops are actually less bug prone. If you have an I and a j variable, you might accidentally replace j with I. With a for each loop, that won't happen. I love C++11. All right, so we're going to say auto ball in, let's see, let's go ahead and store the handle to this grid. We're going to say grid star grid equals, no, sorry, we're going to say, let's do this. We'll say cell star cell equals grid arrow get cell of X and, oh no, what am I doing? Cell star cell equals grid m cells I. I'm trying to do more work than I actually need to. And I'm going to, for now, make it a reference because I can. All right, so for auto ball in cell dot balls. All right, so this is going to loop through all balls in a cell. And what we need to do is check the collision with our ball and a vector of balls. Now remember, we don't want to just loop through every other ball in the cell and update collision with it, because then we're going to check collision with balls that have already checked collision with us, and we're going to check collision with ourself, the current ball. So we actually do need a j. We need a counter. Sorry, int j equals 0. J is less than cell.balls.size. J is less than cell.balls.size. Just make sure you don't replace j with I, j++. What we're going to do is write a function to handle collision between one ball and a vector of balls. And the reason we're doing this is so that we can check collision with all of the other cells easily, and also check collision with our own cell without duplicating any code. So we're going to write another check collision function. We'll say checks collision between a ball and a vector of balls, starting at a specific index, and that's the key. And I'll explain that here in a minute. Specifics. Specific. I'll just right click specific. So void check collision, and we'll take ball star. Yes, ball star ball. And we're going to say std vector ball star ampersand. Always remember the ampersand, or you're going to make a whole copy of the vector, and that's slow as sin. And we're going to call this balls to check, and int starting index. Now the reason we want a starting index, and the only time we're going to use this is when we're checking in the same cell, is because if I pull this over here, let's say we are updating this green cell here. When we're updating this green cell, the red, we'll call it the orange ball, first needs to check collision with the red ball, so it's going to do that. However, we don't want it to check collision with itself. What we're going to do is pass the vector of all balls in here, but we don't want to collide with ourself. So we're going to pass the index beyond this orange ball. So we're going to start at vector index 1 instead of starting at vector index 0. This also has the effect of causing us to not do any duplicate collisions. Orange and red are not going to check collision twice. They're only going to check collision once, because when red goes and it checks collision with the vector, the index after it is the end of the vector, so it doesn't even need to check anything. Pretty nifty. So let's copy that below update collision in ball controller right here. Yes. And we're getting an issue here because we didn't delete grid star grid. Make sure you do that. Okay, so for int I equals 0, I is less than balls to check dot size I++, and I've already made a mistake. It's int I equals starting index. What are we at, like 6 mistakes now? And we're going to say check collision between, and now check collision takes, unfortunately, ball references instead of ball stars. So to do this correctly, we should change those to pointers, or we could be a little hacky, and we can just say star ball, because remember that will get the value pointed to by ball, and it will then be able to be passed in as a reference. And that's fine too, whatever. And the second ball that we're going to check is balls to check I, like that. But again, balls to check is a vector of pointers, so we have to say the value pointed to by balls to check I. All right, and that is that for collision. For our own cell, it's not going to check collision with neighboring cells yet. Well, we have to just implement that. So what we're going to do here is first let's check with our own cell. And to do that, what we're going to do is we're going to say check collision, And for the ball, we're going to say cell.ballsj. And that is, tell me, that's a pointer. Yes, it is. Good. And for, let's see, for the vector of balls to check, we're going to say cell.balls. And for the starting index, we're going to say j plus 1, because we don't want to update ourselves. We want to update everything after ourselves. So this will be update, say update with the residing cell. That works. Now, here's where we're going to update collision with neighbor cells. But just for kicks, let's see what happens for now. We should get some partial collision and hopefully not a crash. Oh, no, we shouldn't, because I didn't actually call that function. We need to call update collision, and we're going to do that here. Update collision with grid. There we go. Obviously, I'm not even going to comment it because it's sure. I'll comment it. Updates all collisions and using the spatial partitioning. All right, now let's run it. Cool. So you can see along grid boundaries, balls are colliding. Now it looks like there may be a bug. Let's see. Each cell is what, 128, and these blue balls are, what do they have, a 64 radius? So we're getting some collision, but there's a lot of bugs. But I think it'll be all fixed once we actually change it so that it checks the neighbors. So let's try that and see if that does fix it. And if not, then I will pause the video. All right, so now to get the neighbor cells, we need to be checking the positions. And let's see, I'm pretty sure we're treating y as going up, and the positive direction is up, but we may have to flip this. We'll find out. So let's, actually it really doesn't matter. So we're going to say if cell.balls. Let's see, position. Let's get a ball handle here so we don't have to call cell.balls all these times. We're going to say ball star ball equals cell.balls I. No, J. That's one thing you got to worry about when you're not using for each loops. Now we can't use a for each loop because we need this j plus 1 here and we need this I here, unfortunately. But otherwise I would say definitely use a for each loop so you can prevent stuff like that. So now we can replace cell balls j with ball. And here we can say if ball.position.x is greater, wait. No, this is actually x. This is the cell that we're currently in. If x is greater than 0, then we can check in the left direction. So this is going to be, all of our left checks are going to be nested in here. And that will be most of the checks. Let's see, we can nest these 3 checks. That's a terrible color. We can nest these 3 checks in that loop, and then we can have one more case for checking this one right here. So first let's check the left. The top left one will be if y is greater than 0. Then we're going to say check collision with ball and get, and let's see, grid.get cell. And the cell we're going to check is x minus 1 and y minus 1. That's the top left. And for the starting index, we're going to say 0. We don't have to worry about checking with ourself because we're just checking with a completely different cell. What's the issue here? No overloaded matches ball star cell star int. What is it? It's ball star. Oh, right. Because it's get cell dot balls, arrow balls. All right, and now let's check for the left one. And for the left one, we don't have to check y. So actually, the left one always happens. Let's just do some comments. Top left, left, and here, instead of y minus 1, we just say y. And we'll do bottom left here. So if y is less than, let's see, grid dot m num y cells minus 1. Yes. If it's less than that, then we can check down. So bottom left, check collision. Instead of y minus 1, we say y plus 1. And let's see, left, top left, bottom left. And finally, we need to check with up. So up cell. If y is less than 0, no, if y is greater than 0, then we do another check collision, except instead of x minus 1 here, we're going to do y minus 1. And now, if all went well, the game should resemble exactly what it did before, but with spatial partitioning, and that is beautiful. I honestly expected some bugs, but there you have it. We have spatial partitioning. So now, let's go crazy and let's see what it does. Let's go to maingame.cpp and crank up the number of balls and see how much better it does. If you remember in the previous video, whenever we had 4,000 balls, it got like 3 frames per second. It was terrible. So let's go ahead and do 4,000 balls. Now we're going to need to decrease the size of our balls for sure because they're not all going to fit. Let's say these, let's just decrease by a factor of 10. So they're going to have a radius of 2, 3, and 5 respectively for the balls. And what we also need to do is whenever we initialize our mgrid here, we want to change the cell size to be, I would think, quite a bit smaller because the biggest radius is only 5. We want it to be probably as small as we can, but again, the smaller it is, the more grid spots we have to iterate through without that optimization. Let's put it at 32 and see what happens. Oh, fingers crossed. All right, so 32 is not good. We're getting 6 frames per second. I'm going to go ahead and pause the video and find out what we can do to make it perform better. All right, so it seems to be that the best value is 12. And when I run it with 4,000 balls, unfortunately, on the video it's showing 11 FPS, but I was only getting about 14 frames per second. Now, this is way, way better than it was before. It was getting probably 2 or 3 frames per second. However, this isn't as good as I was hoping. So what I'm going to try to do right now is pause the video and see if I can do a few optimizations. And if they work, I'm going to go ahead and show you what I did and how we can make it even faster. Alright guys, I played around with a few optimization things. One of them I want to show you in the next video actually, because it's a really useful pattern to use for everything. It didn't really boost FPS at all, though, but it is a good thing to know. One thing I did add that you should probably add is whenever I initialize the grid, after I create all the cells, I loop through and reserve their internal vectors to have a starting amount of storage, and I'm using 20 for that. Because otherwise it's going to keep having to resize that internal memory a whole bunch of times for all of those different cells as the balls move around. Now the reason everything was slow is actually because we were in debug mode, obviously. Debug mode is incredibly slow, and I'm very surprised we got 16 frames per second in debug mode. So let's run it in release. Now remember, before, release mode was getting 3 FPS. So let's run release mode with our 4,000 balls. And lo and behold, we get 62 frames per second. That is absolutely gorgeous. Now let's see just how far we can crank this up. Back to main game. I closed it for some reason. All right, here we are in main game. Let's change number of balls to 20,000. Now I'm hopeful, but I think 20,000 might be overdoing it. Holy crap. So 20,000 balls, 64 frames per second. Now keep in mind, I am running on a pretty powerful computer, but wow, this is crazy. They can't even handle the amount of collision that's going on here. So as you can see, wow, that is so cool. Oh my god, you guys, look at this. I am so amazed by this. So as you can see, spatial partitioning is an incredibly, incredibly valuable tool for increasing the performance of things that have lots and lots of particles and things. All right, let's do even better. All right, let's make a radius of 1, radius of 2, radius of 3. Let's do 40,000 balls. We're really going nuts here. And let's see, I calculated it, and I think with the number of cells we have, it's like 100. It's like 14,000 cells. That's actually not too many to iterate over. But if we make them any smaller, it might be a problem. I'm just going to keep it at 14,000 for now and see what this does. We finally dropped below 60. So this is 40,000 particles, 40,000 balls, all colliding with each other correctly with momentum calculation and everything. and we're getting freaking 40 frames per second, guys. This is pretty cool. So now you know how to make things fast, but we actually are not done optimizing here. There's a few more things we can do to make this faster. Now, the things that we do add are not going to really make a huge difference, honestly. But there are a few things that you should know, a few optimization techniques that you should know that can actually make a big difference in other videos. Now, I have implemented spatial partitioning in the zombie game. However, it's bugged. It was actually really hard to actually get it working in the zombie game, unlike this. That's why I wanted to make a separate game for this. I'm not going to upload that code to you guys just yet because I want to fix the bug when I have the time. But after I do fix that bug, I will definitely upload that code to you so that you guys can play around with a spatially partitioned zombie game. Or if you're feeling a little adventurous, you can implement it yourself in the zombie game. Oh, that's so cool. So they settle down because of friction, and then you can make them go nuts. That's so cool. All right, so yeah, thanks for watching, guys. If you have any questions, please comment. Oh, I need to show you guys a bug real quick that I saw when I was playing around with optimization. When we go down to main game init balls, where is it? Main game init balls. In here, we actually use, here we have I is less than some num balls, and then we do another I variable. Now, the reason this isn't breaking is because this I is replacing, or it's, I don't know, it's just, we should change this to J. We should definitely change this to J. I guess because it's a different type, the compiler's fine with it. It's different scope. But change that to J, definitely, in init balls. Okay, thanks for watching, guys, and I will see you in the next video. I'll try to record it soon. It actually should be a pretty quick video. The next one will be the flyweight programming pattern. Check the description for the code and for a link to some more stuff about spatial partitioning. Thanks.